Okay, so I start this part. Principal stresses on an arbitrary plane with normal n, the traction sigma n can be obtained as this. Yeah, this is interesting. Yeah? How do you consider this? This is there is already there is already a derivation, but I think a simple way to understand this. See, there is some plane, right? Plane, then there is a normal direction. Then there is a sigma direction, which is different, right? This is, not sure. I'm not so sure about this. See, this is something we can consider this this way, right? As we did before. So this triangle part, this is you have some normal, then you have sigma, right? You have area A. Area A. It's complicated. It's complicated. Okay. Maybe this is okay. Sigma I is sigma ij ej. Is this clear? Then sigma. Let's see. Let's do it one by 1, 2, 3. I can do it once. 1, 2, 3. This is 1, 2, 3, right? This is sigma 2. This is 1, j, e, j. This is sigma 3j, ej. Okay. So the n is more like this. N1 sigma 1. This is like sigma n. Sigma n is like this. N2 sigma 2. N3 sigma 3. So you can say this is N1 sigma 1 j ej, N2 sigma 2j ej, N3 sigma 3 J, EJ. Okay? So this is more like this. Ni sigma I, J, E, J. So this is clear, right? Yeah, I think it is completely clear. So I think so the tip to understand this is you can interpret this one like this. This is just like Ni times sigma ij ej. This is much better. I think this is much better. よし。We may resolve this with one component perpendicular to the plane and the remainder tangential to the plane. One component perpendicular to the plane. If you have some plane, there is a perpendicular direction which is normal, and you have a sigma direction. So you can resolve this sigma vector into perpendicular. So this is the perpendicular part. You multiply n. So how do you do this? Okay. So this n is more like n. You can use k, e, k. This is what you can do. So this is inner product goes like ni, nk, ni, sigma ij, ek, dotted with ej. And this part goes like sigma kj. So that then k you can change to j. So you have this sigma ij, ni, and j. For given stress tensor, sigma ij, as the direction of the plane changes, the value of n changes according to the preceding relation. The direction of plane is like this. The direction of the plane is this, nj. The value of n change according to the preceding relation. We can call n the normal stress on the plane. It is important to know the maximum value of the normal stress and the corresponding plane when we design and analyze structures. So we can change this plane in some like you can rotate, for example, rotate in any direction, three-dimensional, and you have to find some plane where the normal perpendicular component capital N become largest. You just find some plane where the value of N become largest. We should find that extremum value of N with respect to Ni with the constraint Ni equal 1. The procedure is identical to the one we used for extremum stretch, and it results in an eigenvalue problem. However, as we will see, the stress tensor is not symmetric. This is a crazy part. Stress tensor is not symmetric. When the body moment L are present, or is a body moment L are present, this fact appears to make this eigenvalue problem different from the case of maximum stretch. But an inspection of quadratic form in N shows that because of the symmetry of Ni and J, its coefficient is sigma ij plus sigma ji. Yeah, you can see here. Here, this is. For example, if you consider summation, you have this term like 1, 2, n, 1, n, 2. Then you also have term like 2, 1, n1, n2. So you have sigma 1, 2 plus sigma 2, 1. Yeah, sigma 1, 2 and sigma 2, 1. Then n1, n2. You always have this term. Coefficient is sigma ij plus ji. Thus, we are free to use the symmetric form of the matrix sigma ij in computing eigenvalues. I'm not sure. Okay, I don't know if we are free to use. Assuming the new matrix is a symmetric version sigma jij, the eigenvalue problem results in the system of equations. So we have this one, right? We have n is sigma ij ni nj, This is more like 1/2 sigma ij plus sigma ji, this is I, n1 nj, and we can call this sigma symmetrized ij n1 n2. Yeah, then this, okay, I say ni nj. Then we can consider this part as eigenvalue. See, we find this some eigenvalue for this sigma n I. Yeah, so hot. Where sigma is the eigenvalue and n is the eigenvector for non-trivial solutions of this homogeneous system, we have to have, so this is the eigenvalue equation, and let sigma k and nk be the eigenvalues and eigenvectors of this problem, multiplying equation 817 by n, ni. Okay. So we multiply this by ni. So here we have ni and ni. We see that eigenvalues are the stationary value of n. How can you say this is stationary value of n? So here is ni is missing. Ni is missing. Again, the three eigenvalues are mutually orthogonal, and these directions are called principal directions and corresponding normal tractions. Sigma k are principal stresses. The three invariants of the matrix sigma ji are something like this. I'm not so sure about this. You got some. We used this eigenvalue problem, right? We had sigma ij nj. This is sigma ni. This is what we got. Then, so the eigenvalue is sigma. So from here we obtain eigenvalue k. Then we also have eigenvector nik. But the question is, which is the principal axis? So we had 3 directions. Normal, okay. Again, the 3 eigenvectors are mutually orthogonal, and these directions are called principal directions, and corresponding normal tractions are the principal stresses. The 3 invariant of matrix sigma ij are something like this. So sure. You have some plane, right? So then you have normal n. Yeah. Then you obtained n equal n dot sigma, right? So I think you obtain 3 planes. So this is given. I think sigma is given. This is given. And for this particular sigma, you have 3 planes. This is also normal. Then there is some sigma. So we call this normal 1, normal 2, then maybe another plane. I don't know how to write another plane. Small, let's say. Another plane like this. So you have n sigma. So this is called sigma 2. This is n2, sigma 2. So you obtain these 3 planes. And these planes are called principal directions, and corresponding normal tractions are the principal stresses. And in these invariants of matrix sigma ij are something like this. Yeah. I can explain you again. Okay. So this is given. Now sigma is given. First you have sigma is given, right? Then this will give us 3 planes, 3 normal vectors. 1, 2, 3, right? Where in these three normal vectors, actually this is a plane. Each of them corresponds to a plane. And in each plane, there is this relation, ij, sigma ij, n, j. This is like a sigma k, n, I. There is such eigenvalue problem. And for this, so this is n. And in this case, the perpendicular component of n, no, this is called, I think, so for each of this, we have sigma as a sigma k. I think it's sigma k, right? So each of them, I'm not so sure. Sigma n, sigma n. So each of them, you have sigma n, sigma 1, sigma 2, sigma 3. Yeah, so I think this is more like eigenvalue. Is it eigenvalue? What I say is here sigma ij is given. Sigma ij is given. And you have sigma 1, sigma 2, sigma 3. This is vector, right? So this n is perpendicular, this vector perpendicular. There is a sigma n, something like this, right? So then there is a principal axis here. So you have to miss, you don't have to miss, you shouldn't miss this one. Okay, I can explain. There is this one. There is this one. N I K. And this part is like sigma K I. Yeah, so the N is this. This is N. N in particular case, N is more like sigma I N dotted with Ni. And this value is called sigma I. So this is sigma Y, sigma 2, sigma 3. Am I right? So this is a vector. So I think here we look. This is a general case. So then we look for N1, Ni parallel to sigma I. This is what we have to find. Then we obtain this one, sigma 1, sigma 2, sigma 3. And these are called principal axes. Okay, so let me stop video here. Now we'll continue shear stress next time.